Hello, today we're going to talk about 2.5 Lewis diagrams, Lewis dot structures, and some exceptions to the octet rule. So Lewis dot structures are really critical for visualizing molecules in covalent structures because of the fact that they show how these electrons are going to be positioned. So I want you to think about atoms in terms of electrons and how they're being shuffled around. So you have an element that has a bunch of electrons all around them. How do you go ahead and predict those shapes? And so a Lewis dot structure really talks about those and how we're going to be using them for visualization of electrons. So the first thing is you want to do is when you talk about Lewis structures is you want to count how many valence electrons you have in each one. So take a look at your periodic table and take a look at what group phosphorus in. Phosphorus is in group 5, and because of that we're going to use 5 valence electrons. Chlorine is in group 7, it has 7 electrons, and then in this case, that is chlorine. And because there's 3 of them, that multiplies it by 3, and that gives us a total of 26. So that's how many electrons are going to be technically shared between phosphorus and chlorine. That brings us to the second part. You always put the least electronegative element in the middle and then connect them across with single bonds. So for example, phosphorus here, it's your least electronegative element because it's a little bit to the left of chlorine. And because of that, we're going to put the chlorines around there. Now, the exception to the rule is hydrogen. Hydrogen is always put on the outside, and it only needs to share 2 electrons. It doesn't need 8. So when you draw hydrogen in there, you're going to basically draw them a little differently. And so what happens here is phosphorus, you have basically 8 electrons, 2, 4, 6, 8. It's going to be right smack in the middle. Next one you're going to do is you're going to complete the electrons by putting them all around, and then you're going to complete them for the octets, except for hydrogen, of course, because it has 2. So phosphorus here is going to have 8, 2, 4, 6, 8. Chlorine is going to have 8, and we represent those with dots around them. Each dot represents a pair of electrons, and what we're going to do is make sure that they share with phosphorus so that chlorine gets 8, phosphorus gets 8. Now the Lewis dot structures, when you add them all up, you're going to end up having to subtract how many valence electrons you have, and if there's any extras in there, what you're going to try to do is you're going to put them as lone pairs. So for example, phosphorus in the other slide did not have 8 here. I think I miscounted. It's supposed to have 6. But then the moment you add in these 2 electrons, you're going to have a total of those 2 lone pairs. Any left over are going to be attached to that central atom with those additional lone pairs. So in this case, because phosphorus had 2 left over to make that 26, it's going to be a lone pair on phosphorus. Next step you want to do is you're going to count the total number of valence electrons in the molecule. So again, for CO2, we're going to do the exact same thing. Carbon is in group 4, so we're going to have 4 electrons. Oxygen has 6, is in group 16. There's 2 of them that make 16 electrons total. We're going to spread them all across and take a look at the least electronegative element. So you already know that carbon is in the center because of the fact that it has only 4 electrons, and it's going to be on the left hand side of the periodic table, while oxygen is in the terminal side. It's going to have those. And because of that, you're going to complete the octets for the hydrogen. So we're going to complete all 2, 4, 6, 8, 2, 4, 6, 8 to complete them, except for hydrogen. But carbon here is going to be left with 4. So the problem here is that if you add them all up and you subtract them, you're going to end up with 0 lone pairs. So if you add up all the electrons you have used and subtract them from the total number of electrons, you actually have 0 lone pairs. So we do not have extra electrons, and carbon's octet is not full. So now what do? We can't add any more electrons. So what we need to do is add a second step. So this is a little different from the other ones because in this case we don't have enough electrons to get into carbon. So what we're going to do is we're going to move multiple bonds, and we're going to move them to complete the octet going to carbon. So what we're going to do here is we're going to move the oxygen atoms over here, and what we're going to do is form what they call a double bond. And the reason we do this is because carbon doesn't have enough electrons to make that octet, and so what you need to do is find another way to get those electrons in. And so in this case, oxygen is going to donate those 2 electrons over here, and then the 2 electrons over here are going to come in that way as well. And as you can see from here, it's going to form 2 double bonds for carbon dioxide, and you're going to get 2, 4, 6, 8, 2, 4, 6, 8, and each one's going to have a double bond for that. Some cases you're going to need to make a triple bond. So a triple bond is very common between usually a nitrogen. So if you see a nitrogen, most likely there's going to be with a carbon. There's usually going to be some sort of triple bond in there. And in this case, you need to make a triple bond because nitrogen needs to have 8, But because your carbon can only bring 4, so 1, 2, 3, 4, nitrogen is actually going to form that triple to make that 6 electrons here. And that's going to be 2 electrons for each line. So when we're talking about polyatomic ions, it gets a little bit more complicated. If you're trying to make a Lewis dot structure for a polyatomic, you must take the charge of the overall molecule in consideration. So here's an example. Iodine comes in with 7 electrons, oxygen comes in with 6, but there's 3 of them, so that gives you 18. But because we have that extra negative there, we're going to add it to the 15 here. So 18 plus this plus 7, and then it's going to give you that 25. We're going to add that 1, it's going to give you 26. So because of that, we put a bracket over it, and we put a negative charge on iodate, which is going to be 26 electrons. Sometimes you're going to have incomplete octet. So boron here does not have the ability to make 8 in this case. So boron generally is going to only have 5 protons. And the reason is because, again, it doesn't have that attraction to those electrons. So this is going to be okay. Sometimes these octet rules are not going to be always the case, just because of the fact that, these elements only have these 5 protons. So you have incomplete octets and it's perfectly fine. Expanded octets are from periods 3 to 7, and those can bond up to more than 8 in their octet. So if you're going down groups periods 3 to 7, you're going to have elements that have higher ways to bond. So the violation of the octet rule is usually in effect. And here's an example of an expanded octet with phosphorus. Phosphorus here has 2, 4, 6, 8, 10. Chlorine obviously keeps its 8, but generally you're going to see phosphorus with more because of the fact that it has the ability to do expanded octets. Another one is sulfur. Sulfur is a very common expanded octet, 2, 4, 6, 8, 2, 4, 6, 8, 10, 12, with fluorines on the sides. And then xenon, which is technically a noble gas, shouldn't technically bond, but it does, has another expanded octet as well. So just keep that in mind when you get to these periods, that you do have exceptions to the Lewis dot structure rules.